Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about deriving mixed Nash equilibria. My name is Rick and my co-teacher, who originally prepared these notes, is Christoph. The plan today is to really just delve into how we can derive this mixed Nash equilibrium that we've talked about in the past. So we're going to start by introducing a general 2x2 payoff matrix. Then we're going to go through the exercise of maximizing expected utility in order to find the mixed Nash equilibrium. And to do that, we're going to do three things. We're going to do this maximization in three different ways. First, we'll do it graphically, so you can kind of visualize what's going on. Then we'll use a standard optimization technique, which is a little bit more formal and requires just a little bit of calculus. And finally, we're going to use a shortcut, and we'll call that the endpoints shortcut. And the idea is that hopefully by doing it these three different ways, one or more of them will kind of resonate with you, and it'll work for you. And so whichever of these makes the most sense to you, you're welcome to keep that in mind. It is important that you kind of understand how this process works in using one of these techniques. Once we've driven home the message of how to use the how to maximize the expected utility and calculate the Nash equilibrium therefrom, then we're going to talk about the interpretation of that result, which is a little bit unusual. And that's it. So let's start by talking about the general 2x2 payoff matrix. Now remember, when I write 2x2, what it means is that there is a player that has two pure strategies, and another player that has two pure strategies. And because of that, there's a total of four combinations or possible outcomes. Before I write down the payoff matrix, let me just recall Nash's existence theorem, which says that every finite game has at least one Nash equilibrium, or NE. So last time we saw a case where there were no pure Nash equilibria, and that motivated us to look at the mixed strategies, and we found that there was a mixed Nash equilibrium. So again, let's set up our problem to look at the mixed strategies. So let's say we've got these two players, and the players, maybe we'll call them maybe Ricky and Chrissy. And we could say that Ricky plays strategy, let's call it Roman 1, with probability P, else or otherwise he plays Roman strategy 2. And that would be with probability 1 minus P. Chrissy plays strategy, let's just say Arabic 1 with probability, we'll call it Q, and otherwise he plays strategy Arabic 2. So we could write down a general payoff matrix for Rick and Chrissy. That would be Ricky and Chrissy. And for Ricky, let's call the payoffs A, B, C, and D. And for Chrissy, let's use Greek letters for the payoffs: alpha, beta, gamma, and delta. So this is the payoff matrix. We could also look at the probabilities of the various outcomes, and that will be useful to us in a minute. So let's write those down. The probability that Ricky plays 1 is P, and the probability of playing 2 is 1 minus P. Chrissy plays strategy 1, his strategy 1, with probability Q, and strategy 2 with probability 1 minus Q. So the probability of being in the top left corner is the probability of both things happening, both players playing their strategy 1, which is probability of P times Q. Probability of being in the bottom left, well, we have a 1 minus P for Ricky to play his bottom strategy, and Q for Chrissy to play his left strategy. And likewise, you can work out the rest. So now we've got the payoffs for all possible outcomes and the probabilities of all of those possible outcomes. And that's nice because it lets us work out the expected utilities for each player. For Ricky, it's just the weighted sum, let's call his expected utility R. It's just the weighted sum of his utilities weighted by the probabilities of them occurring. So the probability of the top left outcome occurring is P times Q, and that if that occurs, he'll get a payoff A. In the top right corner, it's P times 1 minus Q. That's the probability of that outcome, and if it happens, he'll get a payoff of B, and so on. And the same thing applies to Chrissy, except his payoffs are the Greek letters. So in the top left corner, the probability is still P times Q, but the payoff is alpha, and we can work out the rest. Okay, now we need to think about what should Ricky do, and we'll come to Chrissy later. But Ricky, he wants to maximize his expected utility. And so we're going to figure out how we can do that. And we're going to do it in these 3 different ways that I mentioned before. The first way is graphically, which really just means I'm going to draw some pictures and try to convince you of what's going on. So first, looking up at UR, up above here, you should see that there's various points where P enters into it, but in all cases, it's just the first order of P. There's no P squareds, there's no divided by P, there's no square roots or cosines or anything weird. It's just P where it occurs. So that means that Ricky's utility is a linear function of P. And let me make that a little bit clearer. I can write UR and group all the P terms together. So there's a P times Q times A. So that'll be P times Q times A, and we'll pull the P out of the brackets. And in the next term, we'll be left with a 1 minus Q times B, and then there's a minus Q times C, and a minus 1 minus Q times D, and that's all the elements that are multiplied by P, plus there's a few leftover elements. If we reorganize the UR equation, we are still left with an extra Q times C plus 1 minus Q times D. And you should satisfy yourself that what I've just written here is the same as the expected utility I wrote above for Ricky. And if you've done that, then you should see that this corresponds to a straight line equation. UR is like the y-axis. All this stuff in the square brackets is like a slope, because it doesn't depend on P. P is like our x-axis, and everything left over here, again, it doesn't depend on P, so it's like a constant. The only nuance here is that these parameters M and B depend on Q, which you'll recall was Chrissy's strategy, his probability. So M is actually a function of Q, and B is a function of Q. So it was important to notice that UR was always linear in P, and that'll become clearer in just a minute. I'm going to take a little bit of a sidestep right now and basically redraw the payoff matrix in PQ space. And just stay with me for a minute. It'll become a little bit clearer why I'm doing this in just a minute. So what does it even mean to say PQ space? Well, what I have in mind is some kind of flat space, and the limits correspond to our pure strategies. So maybe we have a parameter, I'm going to draw it in a kind of weird way. Let's say we have this parameter Q, which is increasing to the left, and this parameter P, which is increasing to upwards. So that means that P equals 1 is at the top here, P equals 0 is at the bottom here, and Q equals 0 is on the right, and Q equals 1 is on the left. And the reason I drew it that way is to make connections with the original payoff matrix. Let me show you. So what we had is that Ricky plays strategy 1 with probability P. So when P equals 1, then we're in the top of this payoff matrix. When P equals 0, we're in the bottom of the payoff matrix. And likewise for Chrissy, Q equals 1 corresponds to the left strategy here. And Q equals 0 corresponds to playing only the right strategy. So these, the graph that I've drawn below matches the shape of and orientation of this payoff matrix. And recall the payoffs are A in the top left, B in the top right, C in the bottom left, and D in the bottom right. So that was A, B, C, and D. And just to reinforce that, the top left here is when the players are playing strategy 1 and 1. On the right, we have Chrissy playing strategy 2. On the bottom, we have Ricky playing his strategy 2. And so this captures the payoff matrix in kind of a real extended space, where the corners represent these pure strategies and their respective payoffs, and the interior represents some kind of continuum where the players could be playing a mixed strategy. Now, let's extend this by adding a new dimension, which reflects Ricky's expected utility. And for our case, let's assume this ranking of the payoffs. Let's say C is bigger than A and bigger than B, and B is bigger than D. That's not crucial. So this is just something we're going to do to make things easier to see, but it's not essential. It's just a choice we're making right now. The general message will be the same, even if that's not true. So what I want to do is basically lay down this square onto a flat surface, the bottom. So I've just laid that square down. So I'm imagining that this is P equals 0, this is P equals 1, so that we have P increasing here, and this is Q equals 0, Q equals 1, and Q is increasing this direction. So this square is this new square that we've just drawn. And what we're going to do is add a new dimension, and that will be UR, and let's draw UR on this in this three-dimensional space. So D is our smallest value, and that's in the front corner here. Let's say it's at the very bottom. So let's say that's D. And let's say B, which is on the rightmost side here, is part of the way up. Okay, and A again is part of the way up, and let's say C, which is our biggest value, is at the top. Okay, so this is where the bit about linearity comes in. We made the argument earlier that UR is a linear function of P. So as we vary P, U just changes as a straight line. So as it goes from A to C, it has to be a straight line. That's about as straight as I can draw. And as we go from B to D, again, we need it to be a straight line. That's terrible. Okay, let me do that again. And maybe while I'm at it, I'll add a little bit of color. Okay, it's not going to get much better than that. That's not me bragging or anything. That's just like, yeah, I can't draw any better than that. Okay, what we haven't talked about, but maybe you can work out for yourself, is how UR depends on Q. If you do work it out, you'll see it's also a straight line. So we could connect C and D, and we need a straight line to connect those. And likewise, to connect A and B, we should have a straight line. So now we're starting to get a picture of what UR actually looks like. Let me draw some more kind of lines through the space just to kind of emphasize this. It's a plane, but it might be hard to see. So I hope that makes it a little bit clearer. UR is a plane, and its four corners are the values A, B, C, and D. Now, what we want to do is actually look at this from a different perspective. And this will become a little bit clearer why we're doing this in a minute. What I want to do is look at it from the perspective of somebody who's looking at this from this side. So imagine you're on the right looking at this plane UR. And the way we're looking at it now from this perspective, we're looking at P increasing to the right and UR increasing upwards. So the left hand side here is P equals 0 and the right hand is P equals 1. And this whole square is that magenta square that I've drawn out, looking from that side. And instead of looking at the whole thing, I'm going to look at three particular values, or transects. So I'm interested in this case. So that's the back edge of UR, and also the front edge. And let's draw those. So over here we have C, and somewhere around here we have A, and we have a straight line connecting them. Again, that's terrible. Okay, and for the front, we have the line segment BD. It's a beady little bugger. And we draw the line connecting them. That's a little bit better. Okay, and I'll just color them red again to make that connection with what we had before. Oh well. Okay, and now there's one other case or transect that I want to draw. And first I need to make a little bit of an argument. This is kind of the point we're trying to get to, is that for the particular values of C, A, B, and D that we got, we have one case where UR is sloping down to the right, and in the other case, so that the first case was where Q equals 1, so that's one limit, and in the other limit where Q equals 0, we had it sloping up to the right. So the slope actually changes from being negative to being positive. And that is something that is going to be generally true. There are some details that I won't mention at this point, but we'll cover them later. The only thing that's maybe not generally true is how it relates to A, B, D, and C in particular. So let me erase A, B, C, and D. Now we have a more general result that'll give you an idea of how things work. Now, if the slope does switch from being positive to negative, or vice versa, then there must be somewhere in between them a value of Q where the slope is exactly 0. And for us, that looks like on this top right graph, it's probably this green line. That will give a flat, boy, I can't even draw a flat line. Okay, so the main message here, and it's taken a little while to get here, but I wanted to walk through it kind of slowly so you kind of get the vision of how to project these things from 2D into 3D and back into 2 dimensions. So the general result here is that if the slope is negative in one limit and positive in another limit, then there must be an intermediate value where it's exactly 0. And this is a general result. It doesn't depend on what the values of A, B, C, or D are, except in a very special case. But generally, you'll find that there is a special value of Q, we'll call it Q star, where the slope is 0, and the only exception to be aware of is if M isn't actually a function of Q, it's just a constant. There is also another nuance, which I'll just mention now, but we'll talk about more later. It's possible that this Q star isn't within the range of 0 to 1. It could be smaller than 0, or it could be bigger than 1. And we'll talk about what that means later on. But generally, there's going to be a Q star where M is exactly 0. So let's figure out where that is. To figure out where that is, we need to go back to our definition of m, and it was all this stuff here. This is the slope. So it's qa plus 1 minus qb minus qc minus 1 minus qd. Let's write that down again. That's q star a plus 1 minus q star b minus q star c minus 1 minus q star d, and that is all equal to 0 when q is equal to q star, which means we can solve for q star, and we find q star takes on the value of, you should work this out for yourself. I'm just going to write it down. B minus d divided by c minus a plus b minus d. This is the value of q that gives a 0 slope for Ricky's utility, which means that his utility no longer depends on his preference, p, the probabilities that he can choose. So when q is equal to q star, Ricky has no preference for any particular value of p, the probability he can choose. In other words, he's indifferent. On the other hand, when q isn't q star, then Ricky's preference is always to choose p equals 0 or 1, because his utility is just a straight line with either a positive slope or a negative slope. And to maximize that, he just goes to the limit, wherever the utility is highest. Now, what I'd like you to do for an exercise is go through the same reasoning, but for Chrissy. Chrissy has the payoffs alpha, beta, gamma, and delta. Work out what will make Chrissy indifferent. And in particular, the question I have is, what is the value of P star that will make Chrissy indifferent? Okay, you should pause the video here and go through the exercise. Once you've done it, come back and we'll continue. And the answer is gamma minus delta divided by beta minus alpha plus gamma minus delta. Okay, so that's our first derivation to show that there's a special strategies or probabilities that the players can choose that creates this indifference. There's still some nuances that we have to talk about, but before we do that, I want to go through the same derivation in a little bit of a different way, because some of you might prefer this. It might be more natural, or it might just be good to see it in a different way, and the two approaches might reinforce each other. So again, let's try to maximize Ricky's expected utility. This time, the technique we'll use will be a standard optimization technique. If you haven't seen it before, don't be afraid. That's okay. You've probably done something like this in a calculus class, but maybe you haven't heard about it talked about as optimization. We're just talking about finding the maximum of a curve. So let's just recall how that works. Generally, the idea is that we have some kind of function. So we have a curve y that depends on x, and maybe it's does something like this and like this or something. Okay, then we can draw tangents to the curve to find the instantaneous slope, and we'll find that the slope here is positive. If we look over here, then we'll find that the slope is negative, and at the maximum, we find that the slope dy dx is exactly 0. So the extrema, and by that I just mean the max and the min, occur where dy dx equal 0. And as you can see, that gives us both the maximum and the minimum. So it's also true here that dy dx equals 0. So often just figuring out dy by dx and setting it equal to 0, that's enough to tell you you're at either a maximum or a minimum, but not enough to tell you which one you're at. That's not going to be so much of an issue for what we're doing here. and you'll see why in a minute. So that was just a little bit of an aside, just to refresh you on how optimization works when you have a function. You just calculate the derivative. So that's what we should do. If Ricky wants to optimize his utility by changing the parameter he can control, which is the probability p, then he just has to take the derivative dur as with respect to p and figure out what that is and find out where it's equal to 0. So let's go back up to where we defined u sub r. It was way back here. So here it is. And if we take the derivative of all of these terms with respect to p, we'll see it actually comes out pretty straightforward, because in cases where it's just multiplied by p, then we just lose a power of p and we're left with the factor q times a in this first case, and 1 minus q times b in the second case. And very similarly over here, maybe I should just do this. So just I'm going to draw this in and erase it. Take the derivative with respect to p. That's going to cancel a p here, cancel a p here. And in this case, we'll be left with a factor of minus 1. And again here, there will be a factor of minus 1. And that is the derivative. Let's just clean that up. Okay, and let's write that down. So there's the derivative. And if I want to find the optimum, then I set that equal to 0. And that will occur when q is equal to q star, where q star is b minus d divided by c minus a plus b minus d. So that looked a lot easier, didn't it, than doing it the first way, the graphical way. Maybe, but if you're not comfortable with derivatives, then maybe seeing it graphically was more helpful. And you'll see that the result is exactly the same. I mentioned earlier that we can't tell whether this gives us a max or a min. It's actually, you can't really tell, because u is a linear function of p. So when it's flat everywhere. And this is what we saw with the graphical case already, that when we get ur to be flat, so it's independent of p, then it's flat for all values of p. So it's not like this curve that goes up and then it goes down. It's just flat. It's just a straight line straight across. And so it doesn't really make sense to say it's a maximum or a minimum. It's just the value of the function, which is just a constant. So the answer to that is both. And that's because ur is equal to a constant when q equals q star. In other words, it doesn't vary with p anymore. So that makes it a little bit weird. Hopefully seeing it graphically helped you understand that. So again, when q equals q star, Ricky is indifferent. Any value of p gives the same payoff. And again, as an exercise, you should go through the same reasoning for Chrissy and find out what is the condition that optimizes Chrissy's utility. And you should pause the video now, because I'm going to give the answer away. The answer is that Chrissy becomes indifferent, which is maybe not quite the same thing as being at an optimum strategy, but he certainly can't do any better. So Chrissy becomes indifferent when Ricky chooses a strategy such that P star is equal to gamma minus delta over beta minus alpha plus gamma minus delta. Okay, that's our second turn at figuring out where the mixed Nash equilibrium is. We haven't talked about how to interpret this result yet. There's just one more way I want to look at it, and then we can talk about the interpretation. And this one's quite short and easy, but it depends on some of the reasoning that we've done before. So again, we want to maximize Ricky's expected utility. And we'll use our third approach, which I'll call the endpoints shortcut. We've already seen that Ricky's utility is a straight line function of p. So if Chrissy can choose a Q star such that the utilities for the two extreme strategies that Ricky can choose, either p equals 0 or p equals 1, are exactly the same as each other, then that line must be flat. And that's essentially what we saw happening in the graphical analysis, the first approach that we used. So in this graph here, if Ricky gets a value of UR at p equals 0, and then at p equals 1 he has exactly the same value of UR, then the line for UR for any value of p must be a flat line and have 0 slope. It's not rising or falling. So we can use that knowledge, and Chrissy can, in particular, can use that knowledge. He can choose his strategy, Q, to be Q star, to make Ricky indifferent to the two pure strategies he has available. Those are the ones where p is exactly 0 or p equals 1. And how does he do that? He looks at the expected utility for Ricky and says, okay, if Ricky chooses p equals 0 and I choose Q star, I want that expected utility to be exactly the same as if Ricky chooses strategy, the other strategy, so p equals 1, and I play that same Q star. So going back to the definition of UR, it's just a matter of plugging p equals 0 in one side of this equation, and then doing the other side, plugging in p equals 1. When I plug in p equals 0, then we'll see that this term goes away and this term goes away. On the other hand, when I plug in p equals 1, then the second term, or third term, and the fourth term go away. So the first term, I don't know if I said that right. I have to think about that. But anyways, when I plug in p equals 0, then the first two terms in UR will be 0. And the third term is Q star times C now. And the fourth one is 1 minus Q star times D. On the other side, if I choose p equals 1, then the first and the second term remain. So they are Q star times A plus 1 minus Q star times B. And the third and fourth term disappear. And from that, Chrissy can decide, can figure out what value of Q star he can choose. And it's exactly the same as we saw before. B minus D divided by C minus A plus B minus D. Yay, that's the same. Again, as an exercise, do the same reasoning to derive P star. And just to emphasize that point, this technique works because if UR is the same at the endpoints, what I mean is when p equals 0 or 1, then it's also the same for all values of p. And that's because U sub R, is linear in p. Okay, so we've done our analysis 3 different ways. They're related to each other, but hopefully you can see the kind of the connections and the differences between them. And hopefully by doing this in 3 different ways, you've kind of wrapped your head around it and are convinced by the math to see this result. But it's kind of a weird result. I'm not sure how much you noticed already, but we have to think about how to interpret this. So what we found is that Chrissy can choose Q star to make Ricky indifferent. And we saw that from these optimization techniques, these 3 optimization techniques that we did. And that's weird because it's not Ricky who's doing something, choosing value of p that's best for him. It's Chrissy that's determining what Ricky sees. And if Chrissy chooses Q star, then all Ricky sees is a flat utility function that doesn't depend on p at all. And vice versa, Ricky can choose a p star to make Chrissy indifferent. So again, that means that Ricky is in control of what Chrissy sees for his expected utility. And we're not talking about a situation where Ricky gets to choose something. You might be thinking, well, Ricky should choose the strategy Q equals Q star? No, because Q is under the control of Chrissy. So it's hard to say whether this is even an optimization problem because they can't control the parameters that optimize their own utilities. Nevertheless, we are talking about a mixed Nash equilibrium because of this criterion here. If Chrissy chooses Q star to make Ricky indifferent, and Ricky chooses P star to make Chrissy indifferent, then no matter what it means, in the end, the result is still that if they both play their star strategy, so the P star and Q star, then they're at a mixed Nash equilibrium because both of them are indifferent at this point, meaning that they have no incentive to switch. I might be belaboring this point a little bit, but it just strikes me as really kind of creepy and cool. And a little bit weird too, because there's nothing saying that they have to choose P star and Q star. And indeed, like maybe they'll do something different. But this is a strategy where if they should happen to decide to play this pair of strategies to arrive at this mixed Nash equilibrium, then neither of them has an incentive to switch out of that. They might not have an incentive to stay either at that point, but they don't have an incentive to switch. And so it's, I don't know if you can think of it as like a trap or something, but it is at least a Nash equilibrium. It is an important outcome that they might end up playing P star Q star because they arrive at this reasoning and can't get out of this reasoning. We'll talk a little bit more about what this means and how they might get into or out of this mixed Nash equilibrium at a later point for some special cases. But this is the general result. Okay, so that was pretty in depth. There was a lot of math and a lot of techniques. Let's just quickly go over some of what we did. So we looked at a general 2x2 payoff matrix, and we looked at what happens if the players are allowed to play mixed strategies, and we tried to figure out how they can maximize their expected utility. We looked at it in 3 ways. We did a graphical analysis, we did a standard optimization approach, and we used a little bit of a cheat. We'll call it the endpoints shortcut. I only call it a cheat because it relies on on knowing some properties of the utility function that we used in the other techniques, the graphical and standard optimization techniques. Namely, that the utilities are linear functions of P and Q. And doing that, we kept arriving back at the mixed Nash equilibrium. And I tried to emphasize the twist in this, which is that playing the mixed Nash equilibrium strategy makes the other player indifferent. Okay, and that was the main point of going through this, to see how to do this in a few different ways and to highlight that twist. So we're all done with this now, and I'll sign off and see you guys next time. Thanks for watching.